Hi, today we're going to introduce generalized linear models and use them to define linear and logistic regression. So we'll start by defining what a generalized linear model or a GLM is, and then use that to define both multiple linear regression and logistic regression as special cases of this general family of models. Then it will be important to distinguish between additive and multiplicative models, a theme that we'll be returning to several times in this course. And then for logistic regression, we'll define Pearson and deviance residuals and application of the Wald test. We'll start with a brief overview of multiple regression as we covered last week, and then move into linear regression as a generalized linear model and statistical inference for logistic regression as a generalized linear model. Starting with our brief review, you'll recall that we described multiple linear regression as having these two components: the systematic component, where we model the expected value of the outcome variable y given any particular values of the predictor variables x. And it looked like this, with this linear predictor with an intercept and then each of the variables multiplied by a coefficient. And that gives us something that is predicted. So there's no random component here. The random component is added as these residuals, and these are the differences between what we predict and what we observe. Putting it all together, we have that each observation is equal to this systematic predicted part plus our random residuals. And then the assumptions of the multiple linear regression model were compactly described in this little formula here that says that the residuals are independent identically distributed according to a normal distribution with zero mean and a constant variance sigma squared that encompasses all these assumptions of the linear regression. And recall, the one that I think is least commonly appreciated is that this assumption of normality is made on the residuals. It's not made on the x's or even on the y's. And one of the obvious cases where you can have that the y's do not look normally distributed but the assumptions are met would be a case with a binary predictor that has a strong effect on y. In a case like this, you could even have a histogram of y that looked something like this. Totally not normal, but this corresponds to a value of x1 equals 0, and here x1 equals 1. So that after conditioning on the variable x, that is using x1 in your predictor, you have normally distributed residuals around your predicted values of y. So that's linear regression in about 3 minutes. Apologies for that, but it will serve our purposes. We're going to move ahead now and put linear regression into the context of generalized linear models. So in this context, it's just one special case of this broad family of generalized linear models, which is a unifying approach allowing us to fit a number of different models, all brought together by using maximum likelihood estimation methods. Using this approach, we can model many types of data directly using appropriate distributions. So we're not limited to normal distributions of residuals. There are Poisson distributions for count data, a number of different distributions depending on outcomes. And because of this, transformations of y are not needed. So you may be familiar with log transformation or, I don't know, square root transformation of y to provide more normally distributed residuals to fit into a linear regression. It's not needed with generalized linear models. So we again have the random component, which will represent just the way that we did before, which specifies the conditional distribution for the response variable. So I call that the the conditional distribution, meaning that it's conditional on the values of x's. So for one set value of x, this tells us the random distribution of y, the part that we cannot predict. And that can come from any distribution in a so-called exponential family of distributions, and we'll have some examples of this starting today. The systematic component is the linear predictor, and that is exactly the same as what we already saw for multiple linear regression. And then the third part is something really different, the link function, which we'll denote by the function g of something, specifies the relationship between the expected value of the random component and the systematic component, and it can be either linear or nonlinear. So going back to linear regression, we had this model with the observed values of y being equal to the predicted values, or the systematic component, plus the random component, which was normally distributed. In this case, we've already seen what the random component, the systematic component are. They're the same, and the link function here is just what we call the identity link, meaning that when you apply the identity link function to something, you just get that same something back. So in the context of a generalized linear model, that's all there is to it. We have this error component, which is a normal distribution in this case. The systematic component is as always, and it will continue to be like this through generalized linear models. And in this case, the link function is just the identity. All right, so linear regression, it was a bit of a cheap start to generalized linear models because it worked just fine without it. But logistic regression, we really need the generalized linear model framework. Now, in this model, it's going to have a couple of the same components. So we still have a random component, but the random component is going to be different. In the logistic regression model, you'll recall from biostatistics 2, we have a binary outcome like a coin flip or survival or death, something that has two outcomes and a fixed probability of one of those outcomes. So the random component of this model is the uncertainty that remains even if you know the probability of one of the outcomes. So the probability of one of the outcomes is going to be given in this model, this logit of the probability. So probability is the outcome of one of our two options, and the log of p over 1 minus p, this is called the log odds because the probability over 1 minus probability, that's the log odds. If something is 90% probable to happen, then this is 0.9 over 1 minus 0.9, which is 9. So if something is 90% probable of happening, the odds of it happening are 9 to 1. So the log odds are equal to this linear predictor. I'm just going to try to fix the rest of this slide. I see that it's going off the screen a little bit here. Okay, that's better. So the random component of this model specifies that y sub I follows a binomial distribution where the outcome is a binary variable. So you'll recall from your first biostat course, I think, that the binomial distribution is what we see when we have a number of events called a Bernoulli series, where every event is independent and it has the same probability of a success or one of the outcomes. And then the binomial distribution is the distribution of the number of successes in a trial of a certain size. So for a fixed value of the x's and a fixed probability, the random component of this model says that our outcome, our binary outcome, follows that binomial distribution. The systematic component is just the same, the linear predictor, and we have this link function now that is the logit or the log odds function. So just put a slightly different way, the probability of the outcome, so this is for a fixed certain value of the predictors, is equal to the inverse logit of the linear predictor. So what does this logit function look like? It's just a regular function. It's easy. We can plot it. It looks like this. So for probabilities between 0 and 1, as we get close to a probability of 0, the log odds approaches negative infinity. We have this sort of sigmoidal shape, and then the log odds approaches positive infinity as the probability approaches 1. And for a probability of 50%, the odds are 1 and the log odds are 0. And the inverse logit function is just the same thing flipped on its side here with the log odds shown on the x-axis. So you can see this is what the linear predictor gives us. It can give us any value between negative infinity and infinity. And after applying this inverse logit function, as we saw on 2 slides ago, we have to do for getting a probability, it returns for any value of the linear predictor a probability between 0 and 1. So it's convenient that way. Let's look at an example. Here's a data set that you'll have some more time to work in the next 2 lab sessions, the contraceptive use data set. So this is a data set where the outcome is whether the participants are using contraceptives or not, and it has several covariates or predictor variables. There's education, which is either low or high, whether the participant wants more children, which is yes or no, the percent using, this is something calculated, this is the percent of individuals with a particular combination that are using birth control overall, and then stratified by 4 different age groups. If you want more information about this, you can go to this link and see a little bit more about the background behind the data set. So I go ahead and perform a regression here with the outcome of whether the individual is using contraceptives with these 3 predictors: age, education level, and whether the person reports wanting more children or not. And I do this using this GLM function. And this is a bit of a shortcut here because normally our outcome variable just has one value. Like with linear regression, it was just a vector with all of the values. I'm actually creating a matrix here, a 2-column matrix, and this is just a shortcut that you can use for GLM in this case where we don't actually have the indicator value of yes, no for each observation. We have the number of counts for each combination of the predictors. So this part, though, is the same, the model formula that we covered last week. And this is something new. This specifies the family of link function that we're going to use. So we're using the binomial family here and the logit function. This actually isn't the only choice. There are other functions that you can use to fit binomial distributions. So we've got 3 predictors here, no interaction terms, and this is the output that we get. So we have estimates for an intercept, 3 age groups, everything except for the reference group, education low, so education high was the reference level, and wanting more children, so not wanting more children there was the reference level. And we see that pretty well everything is significant. All of these things predict the probability of using contraceptives. There are a number of more things that you can look in here. We'll talk a little bit more about this later and in the next class, like how to interpret these estimates. These are log odds estimates and what these tests are being used here for inference. Also the deviance residuals, and we'll get to all of this stuff. So speaking of deviance residuals, let's talk about residuals for logistic regression. Now, the traditional residuals don't exactly make sense for a binary y, just the outcome minus the expectation. And the first alternative, which is actually very, very similar, is the Pearson residuals. It's very similar because it's the difference between the observed and fitted values, where the observed is a 0 or 1, that's the dummy variable of your y, your outcome, and the fitted value is just the probability, which is a continuous value between 0 and 1. But then they're divided by the standard deviation of the observed value. And this is based on the estimate of the variance of a binomial distribution being normal. Another thing that you covered a little bit in your first year class, I believe. You don't need to know how to calculate this here, but you actually did that in first year, at least if you took your intro biostat with me, how to calculate the variance of a binomial distribution. But it's just a normalized residual that is the most similar thing that you could have to the traditional residuals. The important thing here is if you sum these squared Pearson residuals, it produces a Pearson chi-squared statistic. So that is a potential way to perform an inference test. I'm just glossing over that though, and the main set of residuals that are used, the ones that by default are used on the output of the regression table that you saw, are the deviance residuals. The deviance residuals converge to the Pearson residuals for high degrees of freedom, that is a large sample size, but they have a property that will start making more sense as we start talking about likelihood more. The interpretation that each deviance residual is the contribution of that point to the model likelihood. It's a little bit more complicated than the other formula, but you don't have to calculate this yourself anyways. It will be done by software, but because each deviance residual is the contribution to the overall likelihood, summing and squaring them gives this overall deviance, which is directly related to the likelihood. And likelihood is the workhorse of hypothesis testing in generalized linear models. The likelihood of a model has an intuitive definition. It's just the probability of the observed data given a particular model, which you can write like this. The likelihood theta here is the model, so it's all the parameters that define a model. The likelihood of a model given the observed data is equal to the probability of observing those data given that model. So you can imagine it's something that in absolute terms is not all that meaningful, in that the more data you have, the less probable you are to observe that particular combination of data. So the likelihood is going to, given the same model, just a larger sample size, your likelihood will keep on decreasing. But the difference between the likelihood in two models on the same data is important. And that's related to the deviance residuals by this relationship, that the difference in deviance residuals between two models is -2 times the difference in log likelihood. And that forms the basis for a likelihood ratio test, which is used to assess whether the reduction in the deviance provided by a more complicated model indicates a better fit or just indicates overfitting of by adding extra unneeded variables. And it's the equivalent of a nested analysis of variance test with continuous data. And we'll call this sometimes a nested analysis of deviance. And the basis for doing this test is that under the null hypothesis that the more complicated model is no better than the simpler model. Under that null hypothesis, then that difference in deviance is chi-square distributed with a degrees of freedom equal to the differences in degrees of freedom of those two models. That is the degrees of freedom used by their coefficients. So it's pretty simple to apply likelihood ratio test. I'm fitting here another model I called fit 0 because this is an intercept only model. I didn't use any predictors. Using the same data and the same methods as I did before. And by doing this ANOVA between fit 0 and fit 1, specifying test equals LRT for likelihood ratio test, we get the results. And I'm not going to show the results because it was a little bit long to show on the slide here. But that's all there is to it. And you can use that to test the addition of a variable, whether a fit is better than a let's see this, I call this the null model, which would mean the same probability predicted for everyone. So it's a flexible approach to testing. One other test that is used a lot and is provided in the default output of most regression outputs in R is the Wald test. And it is used for a single coefficient. When you look at a regression output table and you see p-values for each coefficient, same thing in R, in SAS, those come from a Wald test by default. And the basis for this is, as I had mentioned before, that the coefficients under random sampling are t-distributed with n-1 degrees of freedom. And the square of this is chi-squared distributed for a large sample. And either of these can be, either the t-distribution or the chi-square distribution can be used for hypothesis tests on whether a coefficient is 0, is the null hypothesis. And these Wald tests can also be used to construct confidence intervals and standard errors on the coefficient. And when you see the column of standard errors in the output of your regression table, those are based on the Wald test. It's worth noting that the Wald test confidence intervals can provide poor coverage of the actual range of confidence of the coefficient under repeated sampling, even with relatively large samples. So there are approaches based on bootstrapping and other techniques that can provide better coverage. Finally, I want to say something about additive and multiplicative models. Recall that linear regression was an additive model. That is, if we had two binary variables, let's say each with a coefficient of 1.5, and if the indicator variable for the binary variable, if each of them are 1, then compared to the reference groups of 0, that adds 3 to our expected value of y. Linear regression, on the other hand, is a multiplicative model because you saw that to calculate the probability there was an exponential. So in this case, if x1 and x2 are 1 compared to them both being 0, the reference group, it adds 3 to the log of the odds. So then the actual odds ratio increases by e to the 3, which is 20-fold. It multiplies the odds. So that's the end of our lecture for this week. Go ahead and do the lab now. It's an interesting lab. It will use the same data set that we introduced today, and you'll be making a table and doing some visualization of it. Thank you.